Hello everyone and welcome to the class. So today I'm going to talk about stereochemistry of organic molecules, right? So I have been solving questions from your previous years of exam and I have been solved questions from your June 2019. This video will be about stereochemistry of organic molecules. This comes under general organic chemistry topic, and this is one of the important topic from where you can easily expect two to three questions from this particular one, right? So I'll be talking about June 2019 exam in this video. So let's start with it. Now, before going into the questions, let me just tell you about the importance of this topic. First of all, you can easily expect two to three questions from this particular topic, and the questions are very, very simple. Okay, you just need to apply the general knowledge or the general basic knowledge of your organic chemistry to solve these questions. Marks weightage will revolve around 4 to 6 marks because you will not get questions of 4 marks from here. Generally, they are asked of 2 marks itself. Difficulty level of the question revolves from easy to moderate. Why I'm saying so? Because these are very basic, okay, very basic organic chemistry, and that's why I would say the questions were not that difficult. They are easy to moderate, right? So let's talk about the stereochemistry of the molecule, right? So the first question over here from which was asked for 2 marks, and it was asked in your CSIR June 2019 exam. What it says that in the following equilibrium, conformer B is more stable than A when R is, right? So these are two conformations given of cyclohexane. Now you know this thing that cyclohexane has a very stable chair form, right? In the chair form, it is very stable, and you also know that in the chair form, if the substituents are present at the axial position, in that case there is 1,3 axial interaction, and which makes the molecule unstable, right? So that means we generally prefer our substituents to be on the equatorial positions rather being on the axial positions. So axial ones are like generally less stable than the equatorial one. But here the question has been asked in the reverse way. What it says that B should be more stable than A. That means these axial ones are more stable than the equatorial ones. Now this is the only condition where, like, there is just one condition where your axial products or the axial substituents are more stable than the equatorial one, and the condition is that there should be an intramolecular hydrogen bonding. So what is the condition? There should be intramolecular hydrogen bonding. Okay, so among the species given to you in the options, there is methyl, there is fluoride, there is chloride, and there is methoxy group. Now among these, which of the group can form hydrogen bond? That's the main thing which you should know. So you should know this thing that in whole of your elements which are present in your in the like whatever molecules you have, there are just 3 atoms which form hydrogen bonds. The highest hydrogen bonding ability is with fluorine, then comes your oxygen, and the least hydrogen bonding ability is with nitrogen. Okay, so FON, these are the 3 elements which form hydrogen bond. So talking about this particular question, so here fluorine is already given in the option. So this will be the only one which will form intramolecular hydrogen bond. So let me just draw and tell you that what actually will happen. So here, if the fluoride is present on the axial position, okay, if let's say these are the 2 fluorides present on the axial position, so these hydrogen which will be present on the axial positions of on the third position, they will have an interaction. It will be a constructive interaction. Okay, that means there will be intramolecular hydrogen bonding, and this is going to increase the stability of the molecule. Here also in the downside, so what we will say, we will call it as 1,3 diaxial intramolecular hydrogen bond. Okay, so this is the reason for more stability of option number B. The rest others will not form intramolecular hydrogen bonding, and hence they will not form a stable product, right? I think this is clear, right? Let's go to the next one. Okay, so here the question says that the relationship between A and B, these are the 2 molecules given to you. You have to tell relationship between them. Now, if you look upon this, there are 2 things which are needed to be taken in care. The first one is this chiral carbon. Over here in both of them, you have this chiral carbon, and this is the this is the alkene group. Okay, so that is also there. So just write down the conformation of both of them. Now this alkene, since 2 bulky groups are on the opposite side, so the configuration of this will be called as E configuration, right? So alkene has a E configuration, whereas if you go for this chiral carbon, You have to see that whether it is R or S. Now, if you want to check it, you will do it in this way. This should be 1, this should be 2, and this should be 3. And the one which is on this like endo side, we take it as below the plane. So don't worry about that. Just see how this arrow goes. So it goes in the clockwise direction. So it is R. Okay. So it has E configuration. It has R configuration. So we will say that for A we have configuration E and R. Whereas if you go for option number B, again the alkene has the same configuration. It has configuration E, and let's look upon the configuration around this chiral carbon. So this will be 1, this will be 2, this will be 3, and this will be 4. Now again the arrow goes in the same direction, but since fourth priority group is coming above the plane, so that's why this will be S, right? So I hope this thing you all understand, right? So let's write down the confirmation. So it's E comma S. Now, the relationship between these two is obviously diastereomer, right? In case of homomer, they both of them has to be same. Like if it would be E and R, it should also be E and R. Okay. In case of enantiomers, it has to be, if it is E and R, this has to be Z and S. Okay, Z, you know, right? Z, E and Z. These are the two configurations. Sorry, two conformations for your alkene. Yeah. So for enantiomers, it should be ER and ZS. Whereas for diastereomers, it's like ER and ES or any other. Like it can be ZR also. That will also make it diastereomer. So since this is the condition for diastereomer, it is diastereomers. For conformers means if you just rotate any bond and you get this thing. But there is no rotation allowed because you have a double bond over here. So ring flipping is also not allowed. So they are not conformers, right? So it's pretty simple that you have diastereomers as the correct answer. So no need to solve anything. You can just solve in the question itself, right? So that's how this question has to be done. So simple question, asked for 2 marks. One point which I will tell you is that if you have any chiral carbon, okay, chiral carbon next to a conformational isomer, then it is diastereomer. Okay, if you have a chiral carbon next to a conformational isomer, and it should not change, okay, where the conformational isomer remains constant, okay, it remains same. So in that case, it is called as diastereomer. So that's how option number 3 comes out to be the correct option for this. Let's go to the next question then. All right. So there in this particular question, it says that the most stable conformation of the following molecule is. This is the molecule. This is a cyclohexane ring, as you can see. Now, a cyclohexane ring is stable if it is in the chair form. So broad form you can easily neglect. Okay, broad form you can easily cancel them. So the most stable conformation of cyclohexane is chair form. Now, in the chair form, there are two possibilities which are shown in the questions, like in option A and B. If you look upon option number A, there is a repulsion between these methyl groups. Okay, these are called as like the axial repulsions. Okay, the axial repulsions over here. Whereas if you look upon this option, there is no much repulsion. This methyl group is not going to repel it because this particular whole group is not near to this. Whereas these are all both on the adjacent sides, so they are going to repel. Okay, so the bulky groups are coming closer to each other, so there will be higher repulsion in this case. So that's why this is going to lose its stability. The most stable one is going to be second one. So the reason for this is the repulsion between these two methyl groups. All right. So that's how this has to be done. I hope this is much clear to you that how I have solved these 3 questions which were coming from stereochemistry of organic molecules in CSIR-NET June 2019. All right. So let me just summarize everything. So the level of questions, I would say they were easy. Okay. In all these questions, whatever we saw, they all were easy questions. All right. So if I talk about them, one by one, this was the easiest one, I would say. The other one is, again, if you know the confirmation, you can do this question very easily. The third one, this was again an easy question. You just need to figure it out that where the repulsion is and where it is not. Concepts which are used, the first concept which is used is your conformation. Okay, conformation of cyclohexane. Okay, you should know about this. This concept was used in the first and the third question. Whereas the second question was based upon the absolute stereochemistry or absolute conformation, okay, or absolute conformation of chiral carbon. So that was based upon that. Useful tip about is that clear up all your clear up all your basics and solve PYQs to get a good idea of this particular topic. So that's all. Okay, that's all from my side. I hope whatever I taught in this video is clear to you guys and you guys understood it well. So thank you so much for watching this particular video, and I will see you guys in the next video. Till then, have a great day.